Understanding Electronics, 195th episode. This part pertains to microcontroller unit, part 66. Welcome to Hobby Electronics. This week objective: to use 24C256 EEPROM stored alphanumeric symbol in lookup table and pattern read and display in MAX7219 8x8 matrix. The major classification in the display comes in the form of two 7-segment display and dot matrix display. So here the comparison is done. The primary difference is that the 7-segment display lookup table stores 1 byte code to light up individual lines segments for a single character, whereas 8x8 7219 max display lookup table stores multi-byte pattern, typically 8 byte to light up a grid of dots pixel for complex symbol and text. This page shows the core structural differences in 7-segment display and dot matrix. The hardware, target hardware, 7-segment LED arrangement is a figure 8 shape. 64 LEDs are arranged in 8x8 matrix grid. Data per character 1 byte. In 8 byte in the MAX7219 display. Visual resolution. 7-segment display has very low resolution. MAX7219 has moderate 64 distinct pixel dot resolution. Character support. 7-segment display supports 0 to 9 number and very limited basic letters like A, B, C, D, E, F, L, so on. The 8x8 MAX7219 display supports full alphanumeric set, punctuation, custom icon and foreign scripts. 7-segment display control concept maps 1 byte directly to one physical pin segment. Control concept of MAX7219 maps byte to individual rows and columns addressed sequentially by IC chip. 1. 7-segment display lookup table. A 7-segment display uses 7 directional LEDs labeled A to G and 1 decimal point. Because there are only 8 LEDs in total, one single byte represents the complete state of display. The working. Each bit in the byte acts as a hardwired on-off switch for a specific segment. Example, the number 3. To display a number 3, you need segment A, B, C, D and G to turn on. The lookup array in C++, a character array from 0 to 9 looks like a simple list of single byte hexadecimal codes. An example of C++ code is given to display 0, 1, 2, 3 up to this can be extended up to 9 to map the 7-segment display. 2. 8x8 MAX7219 character lookup table. An 8x8 matrix contains 64 LEDs. The MAX7219 integrated circuit manages these by dividing them into 8 rows and 8 columns. To display a single character, you must send 8 separate bytes of data, 1 byte for each of the 8 row or column. Working. The lookup table is a 2D array or a flat array grouped by 8 bytes per character. The MAX7219 sequences through 8 internal register digit 0 to digit 7 to draw a character line by line. Example, a letter A is taken as an example. You cannot draw a clean diagonal line on 7-segment display. On a 8 by 8 matrix, you can define a literal bitmap grid. Lookup table array. Each character requires a sub-array of 8 bytes. Constant byte MAX7219 LUT is a hexadecimal function for A and B character is given. This can be used in any form of coding. Understanding 8 by 8 matrix. To understand how this code works without an electronics background, think of a 8 into 8 LED matrix as a mini light up grid. Here is exactly how those weird looking code turns into letter using 1 on, 0 off. The secret. Hexadecimal is just a shortcut for zeros and ones. The code uses hexadecimal numbers indicated by 0x. Microcontroller reads this as binary group of 8 switches that are either zeros for off or 1 for on. Let us break down the 8 codes listed for letter A. 0, 1C hex, 22 hex, 42 hex, 42 hex, 7E hex, 42 hex, 42 hex, 42 hex. Each code controls exactly one horizontal row of 8 light from left to right. Visualizing the letter A in the grid. On converting hex code into ones light on, zeros light off, the grid looks like this given below. Row 1, 1C hex, 0, 0, 0, 1, 1, 1, 0, 0. This is the top of the A. Row 2, 22 hex, 0, 0, 1, 0, 0, 0, 1, 0. The sides start pushing out. Like that, the entire A is defined. The view in 8 by 8 matrix. By replacing ones with light bulb and zeros with blank space, the letter A instantly appears on the screen. This page bitmap clearly shows the letter B in the grid form. The code, structure and working. MAX7219 lookup table. This tells the computer I am making directory of shape. Each shape is a grid exactly 8 rows deep. Every time you type a letter, the computer looks up the specific stack of 8 rows and flips the 24 mini switches on and off to draw the picture. The MAX7219 has a built-in lookup table. The MAX7219 IC has a built-in lookup table. It only works for 7-segment number display, not for the 8 by 8 grid matrix. This feature is called code B decoding. Understanding how it behaves requires looking at the separate role of numeric display and the pixel matrices. 1. MAX IC with 7-segment display. If you are building a digital clock or a counter, the MAX7219 does have a built-in lookup table. How it helps you? You do not have to tell the chip which individual line to light up. A shortcut. You should just send the raw number to the chip. The internal lookup table automatically decodes it and physically lights up the correct line to show a number 3. Limitations. This internal table only knows 15 characters. The numbers from 0 to 9 and letters HELP and dash. If you plug in a MAX7219 into 8 grid of dots to make a alpha text display, its built up lookup table becomes completely useless. Why? The built-in table knows how to light up 7-segment lines, not dots forming letter like A, B, C or Z. The solution. You must turn off the chip's internal decoder by setting decode mode to 0 in your code. You have to provide your own external custom lookup table in your Arduino or microcontroller or microprocessor program. Data transfer for a 7-segment display with external lookup table. When using a standard 7-segment display with an external lookup table, the data transfer is usually parallel and direct drive, unless you add a shift register chip. The mechanism of parallel transfer. The microcontroller outputs the entire 1-byte character pattern at the exact same time across 8 separate GPIO pins. The process. The code looks up the character, example 3, becomes hex 4F. The microcontroller instantly sets 8 output pins to high or low. The data travels down to 8 parallel paths simultaneously. Each wire linked directly to one physical LED segment to turn it on or off. Volume. Exactly 1 byte is transferred per digit change. Data transfer for 8x8 matrix with MAX7219. The data transfer is done through the serial peripheral interface. First, the address packet is sent and the data in the address is taken out and sent separately to display. For example, the row 1 address and the data, how the LED should behave is the data, and it is sent next. So per row 2 bytes of data is sent. So this works out to 16 bytes of data transfer through the serial peripheral interface. Summary and comparison. This clearly shows the efficiency of the 7-segment display and as well the drawback of the 7-segment display. And the heavy load is on the serial peripheral interface for transmitting and receiving data from EEPROM and to the 8x8 matrix display. Components needed. 8x8 MAX7219 display 1 unit. Arduino Uno 1. Data written EEPROM 24C02 1 number. Jumper wires. Breadboard small 1 number. Circuit diagram with 8x8 with 7219 driver using lookup table in 24C08. Reading only. The complete component connectivity diagram is given. The resistor used is 4.7 kilo ohms, and the module comes with the label and one can connect it easily. follow the instructions. There is two type of 8x8 matrix LED display available. One is called common anode column, another is common cathode column. It all depends how you wire and use the 8x8 matrix display. The code will vary accordingly. MAX7219 IC and display module. When you buy a package, the module from the commercially available source, you will get a completely soldered module as shown in the circuit diagram. This is just the breakup of the component that goes into the module. A PCB with the IC and the 8x8 matrix integrated and soldered in the PCB with the lead-in IO pins. Pin description of MAX7219 8x8 module. VCC, power supply voltage typically 5 volt connected to the power supply positive terminal. Ground connected to the power supply ground or negative terminal. DIN, data input pin, used to send data to the module connected to the digital output pin of the microcontroller system. CS, chip select pin, used to enable disable module, also called as load, connected to the digital output pin of the microcontroller system. CLK, the clock input pin used to synchronize the data transfer, connected to the digital output pin of the microcontroller system. The 8x8 matrix display using MAX7219 can be cascaded one after another. Any number of modules can be integrated. Standard commercially available modules have 4 to 6 displays cascaded and assembled together available commercially. The circuit diagram shows the internal wiring in the MAX7912 module. This is for those who are interested in knowing the circuit diagram of the module. This is the pin diagram of 8024C02 EEPROM. This is same for all the EEPROM in this series. This pin diagram is also valid for 24C256 EEPROM. The circuit diagram of EEPROM configuration configured to address 50H is given here. The UNO connection is given in subsequent slides. Circuit diagram for writing data into the EEPROM is given here. Why the pull-up resistor is needed? The I2C hardware design. The SDA and SCL pin on both UNO and 24C02 are having open drain circuit. This means they can only actively pull the line down to the ground low. They cannot push the line up to 5 volt, that is high logic. How to fix? An external 4.7K resistor constantly pulls the line up to 5 volt. When the chip wants to talk, they will pull the line down. Without them, the line float in an undefined state and the Arduino reads them as 0. This will lead to error in reading and writing. Steps to wire 240C02 EEPROM to UNO. Step 1. Connect A4 pin of UNO to pin 5 of 24C02 EEPROM. Step 2. Connect pin 5 of UNO to pin 6 of 24C02 EEPROM. Step 3. Connect plus 5 volt power line of UNO to pin 8 of 24C02 EEPROM. Step 4. Connect any ground pin of UNO to pin 4 of 24C02 EEPROM. Step 5. Pin 1, 2, 3 and 7 of EEPROM is connected to the ground. Step 6. Connect a 4.7K resistor one end to pin 5 of EEPROM and another end of the resistor to plus 5 volt. Step 7. Connect 4.7K resistor one end to pin 6 of EEPROM and another end of the resistor to plus 5 volt. Steps to wire 240C02 EEPROM to UNO. Step 1. Connect A4 pin of UNO to pin 5 of 24C02 EEPROM. Step 2. Connect pin 5 of UNO to pin 6 of 24C02 EEPROM. Step 3. Connect plus 5 volt power line of UNO to pin 8 of 24C02 EEPROM. Step 4. Connect any ground pin of UNO to pin 4 of 24C02 EEPROM. Step 5. Pin 1, 2, 3 and 7 of EEPROM is connected to the ground. Step 6. Connect a 4.7K resistor one end to pin 5 of EEPROM and another end of the resistor to plus 5 volt. Step 7. Connect 4.7K resistor one end to pin 6 of EEPROM and another end of the resistor to plus 5 volt. The complete wiring diagram of 24C02 with Arduino Uno for writing and reading purposes is given in this page. Circuit diagram of EEPROM wired to the Uno is given. The A0, AD0, AD1, AD2 decides the address for communication in the SPI bus with the EEPROM. This is the photograph of the testing bed developed in breadboard using Arduino Uno and 24C02 EEPROM. Hardware connection. This deals with the MAX7219 module connection with the Arduino Uno. VCC is the Uno connected to the Uno plus 5 volt power supply. GND of the MAX7219 pin is connected to ground pin of the Uno. DIN is the data in pin of the MAX7219 and it is connected to pin 11 of the Arduino Uno. CS is the chip select in the MAX7219 module and it is connected to pin 10 of the Arduino Uno. CLK is the clock pin in MAX7219 and it is connected to pin 13 of the Arduino Uno to send the clock pulse. The MAX7219 LED dot matrix module connection with the Arduino Uno is given in this page. This page shows the Arduino Uno and the MAX7219 module to module wiring. Step 2, hardware wiring. Adding the 24C08 or 24C256. The MAX7219 matrix exactly wired as mentioned above. Place your 24C02 or 24C08 or 24C256 IC on the breadboard and connect to the UNO using this map. The power and address pin. Pin number 8 is connected to the 5 volt. Pin number 4 of EEPROM connected to the ground of UNO. Pin 1, pin 2, pin 3 of EEPROM connected to the ground of UNO. Pin 7, right protect connected to the ground above UNO. The I2C communication pin. Pin 5 of EEPROM is connected to pin A4 of UNO. Pin 6 of EEPROM is connected to pin A5 of the UNO. Pull-up resistors crucial. Connect a 4.7 kilo ohm resistor from pin 5 of EEPROM to plus 5 volt. Repeat the same for the pin 6 also. These pull-up resistors are needed for error-free data communication. The C++ code for flashing EEPROM with the lookup table. This is the page 1 of the 8-row hex dump per character defined as an array variable. This is the page 2 of the 8-row hex values for the character designed in array. This is the 8-row hex character set value that defined as an array. This page, the ASCII value from 97, which is depicting small a to the symbol dash, is coded as a hex value for 8 rows. In this section, small j to bracket and ASCII 126 value is defined as a row array for in the hex format. This page contains the setup which initializes the EEPROM and writes the data into the EEPROM, and the loop section is kept empty. On booting, the code is executed only once and all the data set is written into the EEPROM. The screen image of Arduino Uno IDE while flashing is shown in this page. Working of the CPP code is given in this section. Working overview. This is an Arduino C++ kit designed to permanently store 8x8 pixel bitmap text font into an external I2C EEPROM chip, specifically 24C256 chip starting at the memory address 0. Here is the comprehensive breakdown of how this code works. Key components and libraries. The wire.h, pgm space.h, and are the libraries used to for writing into the EEPROM. The EEPROM I2C address is set to 50 hex. The font data matrix. The full ASCII font array holds the visual layout for 96 standard printable ASCII character starting from space 32 address to title address number 126. Prog-mem. This is a modifier forces the massive font array to stay inside the flash memory so the Arduino doesn't run out of the dynamic RAM structure. Each character is represented by sequence of 8 bytes. Each byte represents one horizontal row of 8 pixels. For example, looking at the character hyphen. Hex 18 is the binary for 0001 1000, 2 pixel lit in the middle. Hex 0 is the binary for 000 0000. The empty row creates a gap before the dot. Addressing loop, for loop. The outer loop runs 96 times once in every character in the array. It begins an I2C transaction targeting the device hex 50. It splits the 16-bit current address variable into two 8-bit high byte and low byte and sends them first. This tells the EEPROM exactly where to write the upcoming data. Data transmission. The inner row loop runs 8 times. Because the data lives in flash memory, it uses PGM read byte to retrieve the byte safely. Write B loads the byte into the Arduino I2C buffer. Hardware committing. Wire.end transmission pushes the buffer out over the physical wire. Current address plus equal to 8 increments the memory location pointer by 8 byte, cleanly setting up the boundary for next character. Delay 12 provides a crucial physical pass. EEPROM chip require roughly 5 to 10 milliseconds to permanently write data to their internal memory cell. Without this pass, Arduino would flood the chip and corrupt the file saved. The loop function. The loop block is empty. Once the setup finishes writing all the 96 characters, the program stops doing task and sits idle. The C++ code to read and display in 8x8 matrix is given in this section. The code in this page initializes the wire pin for SPI serial peripheral interface transaction and send max subroutine is initial. This page contains display character from EEPROM subroutine. The address from C32 to 126 is sent to the MAX7219 IC, and the received data is displayed in the matrix. This page contains the setup section and the loop section. All the page 4 codes are copied and put into the Arduino IDE editor and compiled. The flashing process is captured in this page. The working of the read and display code. The reading overview. The code acts as a companion to your previous sketch. It reads the 8-bit font character design out of I2C EEPROM 24C256 and directly streams them into a MAX7219 8x8 LED matrix display to show a scrolling or a flashing message. Here is a line-by-line breakdown of how the display system works. Section 1. Hardware pin configuration. The serial peripheral interface requires 3 fundamental pins: chip select, data in, and clock. These pins are initialized in this section. The UNO pin 10, 11, 13 are used for this SPI bus function. The EEPROM address point to the exact I2C address used in your wiring code, that is hex 50. Section 2. Talking to the display. MAX7219 matrix driver chip needs 16 bit of data at a time. An 8-bit address register which gives the information on the row setting, and the 8-bit data byte which turns the LED on or off. The function is given below. The initialization section 3. The code is given in the setup. Before displaying the text, system optimizes the components and configures MAX7219 display registers with the code given below. Understanding 40000L command. The 4lakh-L command increases the I2C bus speed from default 100 kHz to 400 kHz. This speeds up the data extraction from EEPROM to ensure fluid display updates. The following are the codes given in this section. Section 4 deals with the dynamic data fetching. This is the main brain of the code. When you pass a character like 8 to this function, step A, the address match, unsigned integer EEPROM address is equal to unsigned integer C minus 32 star 8 is the address location. Because the first font item stored in the EEPROM was space ASCII 32, subtracting 32 converts the character into 0 base memory slot index. Multiplying by 8 calculates the precise absolute byte address where that character data begins. Step B, pointing to EEPROM memory. The code in this section addresses the EEPROM and fetches the data from the EEPROM. The step 4C, streaming directly to the matrix. The following the lines stream the data received from EEPROM to the 8x8 matrix. Wire request from 8 tells the EEPROM to split the 8-byte sequentially. The for loop reads each byte from I2C buffer and immediately pushes it directly to the MAX7219 matrix display. The row 1 maps the index 0 to 7 to hardware rows 1 to 8. Section 5, the main execution loop. The code given in the execution loop. The output. The code cycles through the letter TEST space hash 123. Each single character stays completely static on the screen for 800 milliseconds before being overwritten by the next. All the page code of read and display is copied and put into the Arduino IDE and compiled and uploaded. The flashing process is captured in this page. Image of the X displayed in the 8x8 matrix with the complete EEPROM and UNO wired to the display is shown here. The cost of the kit is approximately 540 rupees. The GST and packing courier charges extra. One can contact the author for tips, support, assistance and guidance. Please contact for code and support. Kits are available for learning. Projects for schools and colleges can be designed. Contact the YouTube owner. subscribe to my YouTube channel. Please subscribe to my YouTube channel by following the link. Thanks for watching. See you in the next episode.